Look around you. Seriously, take a moment. Chances are you're either standing on it, walking by it, or maybe even sitting within its embrace right now.
Mm-hmm.
From the bustling sidewalks we walk on every day to the towering skyscrapers that, define our skylines and the bridges spanning our rivers, there's this one material.
Everywhere.
Exactly. It's quiet, steadfast, underpinning nearly everything.
Yeah.
Often unseen, often unheard, yet it is undeniably the most widely used man-made material on Earth.
Quite staggering when you think about it that way.
It really is. Welcome to the deep dive. Today we're plunging into the soul of the material, concrete, our mission, to journey through its remarkable past, examine its profound present, and, well, peer into its complex future.
That's quite a story.
It is. We'll uncover how this humble mixture of stone, sand, and paste has not just supported but completely reshaped our built world. This isn't just geology or engineering, you see.
No, it's much more than that.
It's about the very stuff holding our civilization together, the foundation of modern existence. Understanding it offers, I think, really profound insights into our history, our ingenuity, and where we might be heading. I found some genuinely surprising things researching this, and I'm excited to share this journey, uncovering the stories hidden in something we often just walk on.
Looking forward to it.
Now, when we talk about concrete, most people probably picture, modern building sites, giant mixers, steel frames.
The usual image, yeah.
We tend to think of it as a relatively modern thing, maybe from the last century or two.
Yeah.
But the real story, its enduring legacy, actually starts way back with the ancient Romans.
Mm-hmm.
And what's absolutely fascinating here is just how far ahead of their time they were.
Yeah.
Their approach to building, their materials. It's kind of mind-blowing.
Indeed, it's a common misconception that concrete is purely modern. But you look at sources like Viollet-le-Duc or Palladio, and they make it crystal clear. The Romans were, without question, masters of structure. Viollet-le-Duc makes this really sharp observation. He says the Romans, they kept the core Roman part, the structure itself, but then they focused on modifying the decoration.
Ah, interesting. So function first, then form, or rather integrating them.
Exactly. It points to this deep, practical, incredibly sophisticated understanding of how to make things hold together and last.
So different from the Greeks then. I always picture Greek temples with those iconic columns.
Very different, yes. The Greeks often focused on that vertical support columns, holding up heavy stone beams, the lintels, a very direct load path.
Okay.
The Romans, though, they embraced something else, something more dynamic. They really championed the arch, and later, the vault.
Right. The arch changes everything for spanning spaces.
Completely. Viollet-le-Duc praises their bold essays in construction. He calls them systematic and, crucially, the result of calculation and reason rather than of caprice and fancy.
So engineered, not just built by eye.
Precisely. This wasn't guesswork. It was applied engineering, methodical, deliberate. It let them achieve things architecturally that were just unimaginable before. These huge, open, interior spaces.
Without columns cluttering everything up.
Exactly. A real departure from the Greek approach. This systematic, reasoned method let them really push the boundaries of scale and form.
They sound like brilliant engineers. But, even with that clever design, it must have been incredibly labor-intensive back then, right?
Mm-hmm.
Relying on local materials, manual labor. How much did that limit them compared to industrial processes later? And what were the materials? What gave their structures such staying power?
That's a great question about the practical side. Yes, the labor was immense, but their specific concrete opus caematicium, they called it, actually streamlined things in some ways.
Oh, how so?
Well, it meant they could build massive, complex shapes without needing to quarry and perfectly cut gigantic stone blocks like, say, the Egyptians or the Greeks did.
Ah, I see. Less precision carving needed for the bulk.
Right. They could mix and pour, using far less skilled labor for the core of the structure. The finishing work was still specialized, of course, but it meant they could build faster and bigger than ever before.
Okay, that makes sense. But what about the material itself? What made it so special?
Right, it wasn't just the design, it was the material science. Palladio, who studied these ancient buildings obsessively, guided by Vitruvius, he noted he found not anything which was not done with reason and beautiful proportion.
Reason and proportion again.
And that extended to materials. He describes Roman walls, for instance, with peperino, that's a volcanic rock on the outside, and then baked stone inside temples. These inner walls were key, supporting the vaults, often decorated with stucco.
Okay, so layers. But what was the binder, the cement part?
Ah, the secret ingredient. It was something called pozzolanic ash. This ash found mostly near volcanoes, like around Pozzuoli near Naples.
Pozzolana, hence pozzolanic.
Exactly. It contained silica and alumina. When they mixed this ash with lime and water, it kicked off a chemical reaction. It formed this remarkably strong, durable binder. Critically, it could even harden underwater.
Underwater, wow. So it wasn't like modern cement drying out.
No, it was a hydraulic cement reacting chemically with water, a natural one. This unique property is why their structures have lasted 2,000 years, even in really challenging places like harbors.
That's incredible, just this local volcanic ash unlocking all that. So thinking about those vast, uninterrupted spaces you mentioned, how did that actually change Roman life? What were the societal effects?
Oh, it was revolutionary, not just engineering, but urban design, society itself. Think about the huge public baths they could build, the markets, the basilicas.
Places for huge crowds.
Exactly, massive column-free spaces that fundamentally reshaped public life. Grand gatherings, commerce, civic debate, all on a scale never seen before. It's hard to overstate how this one material and their mastery of it enabled the very fabric of the Roman Empire's public infrastructure.
Can you give a specific example?
The Pantheon in Rome, built around 126 AD. Its dome. It's still the largest unreinforced concrete dome in the world today.
Unreinforced. That's astonishing.
Roman ingenuity.
Yeah.
They varied the aggregate, the stones in the mix. At the bottom, heavy basalt. As they went up, they used lighter stuff pumice, even hollow pottery jars near the top.
To reduce the weight. Clever.
Extremely. Reducing the stress. It wasn't just building, it was advanced material science, perfectly calibrated. Even the oculus, the hole at the top, it's not just for light. It structurally relieves tension right at the weakest point.
Wow. Okay. And beyond these grand buildings.
Well, think about the aqueducts. Miles and miles of channels bringing water to cities. Many still stand. The durability, the waterproof nature of their concrete was essential.
Right, carrying water reliably.
And maybe even more amazing marine structures, piers, breakwaters, harbors built right in the sea. That pozzolanic concrete actually reacted with the salt water to become even stronger.
Stronger in seawater. That defies intuition.
It does. Creating these underwater foundations that have just endured for centuries, this moldability, this durability, it allowed these huge spaces free from the forests of columns you saw before. True pioneers. And then, tragically,
After the fall of Rome.
yeah, much of that knowledge was just lost for almost 1,000 years, waiting to be rediscovered or really reinvented.
It really is incredible thinking about Roman concrete lasting millennia. But like you said, their special mix relied on that volcanic ash, geographically limited.
Exactly. You needed to be near a volcano, basically.
So the world needed something more. Universal, reproducible, to really unlock concrete's global potential. And that brings us, I suppose, to the 19th century, a pivotal moment that turned this ancient idea into the stuff we see everywhere today. So what was the big game changer for our modern world?
That pivotal moment, the real catalyst for modern concrete, was definitely the invention of Portland cement. It was a huge leap. It let concrete move beyond those specific natural pozzolans to a binder that could be consistently manufactured anywhere with reliable properties.
And why Portland cement?
The name actually comes from its resemblance, once hardened, to the high-quality limestone quarried on the Isle of Portland in England, a very durable building stone.
Okay, makes sense. Who came up with it?
It was a British bricklayer, Joseph Aspdin. He patented it back in 1824.
A bricklayer, not a scientist.
Well, an innovator. He figured out that by carefully burning finely ground limestone and clay together in a kiln at really high temperatures.
Like super hot.
Very hot, yes. Then grinding the resulting clinker, as they call it, into a fine powder. This powder, when mixed with water, hardened significantly, much like that Portland stone. This predictability, this consistent strength and durability was exactly what the Industrial Revolution needed for its massive projects.
Right, for railways, factories, bigger buildings.
Exactly. And our sources, like Building Codes Illustrated, they define modern concrete very precisely now. A mixture of Portland or other hydraulic cement, water fine aggregate and coarse aggregate with or without admixtures. That standardized formula, industrially reproducible, that was the revolution.
That definition seems straightforward enough. Cement, water, aggregates. But you hear people talk about concrete curing, not just drying. And you mentioned earlier, it's not inert. For most of us, concrete is just a hard block once it's set, solid, unchanging.
Right, that's the common perception.
But if it's this dynamic chemical process, why does it feel so permanent? Does the chemistry eventually stop? Or is it always subtly changing, even centuries later? Can you unpack that for us? It sounds way more complex.
Okay, yeah, let's dive into that. It's genuinely fascinating and definitely misunderstood. You're right, it's far from inert. Think about how Lavoisier showed fire wasn't a substance, but a process.
Right, a chemical reaction.
Exactly. Concrete's similar. It's not just a static mix that gets hard. It's an ongoing chemical process. It doesn't just happen once. It continues evolving for decades. The cementitious materials, as the books call them, they bind it and other aggregates together with a cementing action.
Okay, so cementing action implies chemistry.
Precisely. The key reaction is called hydration. When you mix water with cement powder, the water doesn't just evaporate, leaving dry stuff behind. No, it chemically reacts with the cement particles.
It becomes part of the structure.
Yes, it forms a new, hardened paste. This hydration reaction actually consumes the water, forming an incredibly dense, interlocking microscopic structure. It's a calcium silicate hydrate gel, usually called CSH gel.
CSH gel.
Think of it like an incredibly strong 3D molecular glue. It coats aggregates the sand and gravel and binds everything together. That's where concrete gets its amazing strength and durability. It fundamentally transforms water and powder into solid rock.
So it's not drying, it's hydrating, consuming the water chemically.
Exactly. And there are byproducts too. Calcium hydroxide is formed, and over time, reacting with CO2 from the air, that can form calcium carbonate, a process called carbonation, which makes it even harder. The whole thing generates heat too, the heat of hydration, sometimes quite a lot in big pores, which has to be managed.
Right, to avoid cracking.
And it's not instant. Hydration is a slow burn, a gradual chemical change. Concrete keeps gaining strength for years, even decades, as long as moisture is available for hydration. So yes, it is subtly changing chemically for a very long time, although the rate slows down dramatically after the initial curing period.
Decades. So it really is kind of a living material, chemically speaking.
In a way, yes. That's why managing water and temperature during curing is so critical.
Which brings us back to the construction site. Managing this ongoing chemical dance, especially with weather, scale, it sounds like it needs incredible precision. How do builders handle that?
It really is both an art and a science. Meticulous attention is key. Placement and curing are absolutely critical phases. Fundamentals of residential construction gives that image of a worker directing concrete into footing forms with a hose from a pumper truck.
Right, showing how versatile it is for complex shapes.
Exactly. It can be delivered precisely where needed, but just getting it there isn't enough.
What else? Admixtures, I've heard that term.
Yes, admixtures are crucial for modern concrete. These are chemicals added in small amounts to tweak the properties, like plasticizers make it flow better without adding too much water, which would weaken it.
Okay, more workable.
Right. Or retarders slow down the setting time, useful in hot weather, or for really big, complicated pours where you need more time to place and finish it.
And accelerators for the opposite, cold weather.
Exactly. Speed up setting, get strength faster. And air entraining agents, they create microscopic air bubbles. Sounds weird, but it massively improves resistance to freeze-thaw cycles, critical for roads, sidewalks, anything outdoors in cold climates. These let engineers really fine-tune the concrete for the job.
Okay, so the mix is optimized, but then comes the curing. You said premature drying is bad.
It's a major hazard, especially as the source says in hot or windy weather. If that surface water evaporates too fast before hydration gets going properly, a slab can crack even before it begins to cure.
And that's not just cosmetic, right? It weakens it.
Definitely. It compromises the structural integrity right from the start. So builders have strategies. They might spray on a curing compound like a sealant to trap moisture inside.
Or cover it up.
Yes. Use sheets of paper or film. Plastic sheeting, basically. Or wet burlap blankets, constantly kept damp. Sometimes they just leave the wooden forms on longer, anything to keep that moisture in.
So it's not about drying it fast, it's about drying it slowly, or rather keeping it moist.
Precisely. It's about controlling moisture loss. Ensuring the cement has enough water available to fully hydrate, to complete that chemical reaction, so the concrete reaches its designed strength and durability. It's like nurturing that chemical process for the long haul.
Okay, so we have this incredibly strong material thanks to Portland cement and careful hydration. It's versatile, durable. But you mentioned earlier it has an Achilles heel. It's not perfect on its own for every structural job. And that's where reinforcement comes in. Thinking back to the Romans, even with their amazing pozzolanic concrete, what were the fundamental limits they faced that modern reinforced concrete overcomes?
That's the crucial difference, really. Plain concrete, even the best Roman stuff, is fantastic under compressive forces. You can squeeze it, stack weight on it. It's incredibly strong.
Resist crushing. Got it.
But, and this is the big but, it's relatively weak under tensile forces, pulling forces, stretching forces.
Like bending.
Exactly. Try bending a plain concrete beam, even a thin one, it'll just snap. Microcracks spread really easily under tension. So the big question for engineers became, how do you build things that resist both crushing and pulling? How do you make longer bridges, thinner floors, cantilevered balconies?
Things that inevitably involve bending and tension.
Precisely. And the answer, as Building Construction Illustrated points out clearly, is tensile reinforcement. Adding something strong in tension to the concrete, that synergy unlocks its true potential way beyond what arches and vaults alone could do.
So tensile reinforcement, what does that actually look like in practice? And how did this idea, especially using steel, become so fundamental?
Well, the primary method, the one you see everywhere, is using rebar, short for reinforcing steel bars.
The steel rods you see sticking out of concrete foundations.
Exactly those. These bars are embedded inside the concrete, placed strategically where engineers calculate tensile forces will occur. The concrete handles the compression. The steel handles the tension. Together, they form a composite material, reinforced concrete, far stronger and more versatile than plain concrete.
A team effort.
A perfect team effort. It lets architects and engineers design much longer spans, thinner elements, more complex shapes. Things impossible with unreinforced concrete.
When did this idea start? Was it right after Portland cement?
Not immediately, but it followed relatively closely in the mid-19th century. Interestingly, one of the pioneers was a French gardener, Joseph Monnier.
A gardener. Again, like the bricklayer.
Yeah. He started experimenting by reinforcing concrete garden tubs and planters with an iron mesh to make them stronger.
Humble beginnings.
Very. But the science evolved quickly from there. Now, rebar comes in different grades, indicating its strength, how much tensile force it can take before yielding or stretching permanently. Like grade 60 means 60,000 pounds per square inch yield strength. That steel strength, protected by the concrete, makes an incredibly robust system.
And placing it correctly is crucial, I imagine.
Absolutely critical. Building Construction Illustrated gets specific, like saying reinforced walls might need no 3 bars minimum at 12 inches on center for each layer. Engineers calculate precisely what size bar, how many, and exactly where they need to go to handle the expected stresses.
And those ridges on rebar, are they important?
Very. Those deformations create a mechanical bond, locking the steel and concrete together so they act as one unit. Prevents the steel from just slipping inside the concrete when stressed.
Okay, makes sense. But it's not just about putting steel in it, right? You mentioned protection.
Right. Placement and protection are vital for long-term performance. The sources talk about minimum cover. That's the amount of concrete between the rebar and the outside surface.
Why is that cover so important?
2 main reasons. First, protection from corrosion. If moisture and air get to the steel, it rusts. Rusting steel expands, which cracks the concrete around it, weakening the whole structure. The concrete cover acts as a physical and chemical barrier.
Okay. Prevents rust. What's the second reason?
Ensuring proper bond. You need enough concrete around the bar to effectively transfer the stress between the steel and the concrete. The amount of cover needed depends on the exposure, more cover if it's exposed to weather or soil, like maybe 34-inch inside, but 1.5 or even 2 inches if it's outside or underground.
So more protection for tougher environments.
Exactly. And for thicker walls, say over 10 inches, you often need 2 layers of rebar, one near each face, for better crack control and strength.
It really is a precise science. But what about really big projects? Huge bridges, super long spans. Is standard rebar enough for those extreme cases?
That's where we get into even more advanced techniques. Pre-stressed and post-tension concrete. They take that steel-concrete synergy to another level.
Pre-stressed, how does that work?
Okay, in pre-stressed concrete, they use high-strength steel tendons or wires. These are stretched, put under tension before the concrete is poured around them.
Stretched first.
Yes. Then they pour the concrete. Once it hardens and gets strong enough, they release the tension on the steel tendons. The steel wants to spring back to its original length, right?
Yeah.
As it tries to shorten, it squeezes or compresses the concrete around it. It basically puts the concrete into a state of pre-compression.
So it's already squeezed together before any load is even applied.
Exactly. This built-in compression counteracts the tensile forces that the beam or slab will experience later under load. It makes the concrete effectively much stronger in tension.
Clever. And post-tensioned. Similar idea.
Similar principle, but done differently. In post-tensioning, they place ducts or sleeves inside the formwork before pouring the concrete. After the concrete hardens, they thread steel tendons through these ducts. Then, they use hydraulic jacks to stretch the tendons after the concrete is already hard and anchor them at the ends. This also squeezes the concrete, inducing that beneficial compression.
So before pouring, after pouring. What's the advantage?
Both allow for much longer spans, shallower beams, thinner slabs, think bridges, parking garages, high-rise floors. You can achieve the same strength with less material, lighter structures, more open space. It's incredibly efficient.
Wow. So this whole reinforcement thing is fundamental.
Absolutely. It's so critical that, as one source points out, rebar installation is often a major constraint in the construction schedule. Rebar installation prior to concrete placement dictates the workflow. You can't pour until the steel is perfectly in place. It's the step that transforms concrete from strong but brittle into the robust, versatile structural backbone of pretty much everything we build today.
So we've established concrete's amazing structural power, especially with reinforcement allowing these incredible forms. But it's not just about strength, is it? Concrete has also become this huge medium for artistic and functional expression.
Oh, absolutely.
It seems so versatile, almost like clay for architects. It feels like it's moved way beyond just being a structural workhorse.
It really has. And it's interesting. Le Corbusier, the famous architect, he drew this distinction in Towards a New Architecture. He says the purpose of construction is basically to make things hold together, simple function.
Right. Keep the rain out, stop it falling down.
Exactly. But the purpose of architecture, he argued, is to move us, to create an emotional response, a connection. He felt architectural emotion happens when a building rings within us in tune with a universe.
Deep stuff. How does concrete fit into moving us?
Because of its formability. It bridges that gap between pure function and artistic expression like almost nothing else. Its ability to be cast into virtually any shape curves, complex geometries, whatever the architect dreams up allows for that emotional impact. It can achieve things solid stone or timber just can't. It's like liquid stone, you pour it, and it becomes the vision.
Liquid stone. I like that.
Le Corbusier himself was famous for using béton brut raw concrete.
Brutalism. Right. That style gets a mixed reaction.
It does, but his idea was to embrace the material honestly. Show the marks from the wooden form, celebrate its raw texture, its structural integrity. His Unité Habitation building in Marseille is a classic example. Monumental, exposed concrete.
Some find it cold, though.
Some do. But for Le Corbusier and others in that movement, it was about truth to materials, the sculptural power of concrete. He also talked about the mass production house, seeing how concrete could impose unity, consistent windows, doors, construction methods.
Standardization for efficiency, but maybe also aesthetic coherence.
Exactly. Not necessarily bland uniformity, but a deliberate, integrated design language made possible by the material's consistency and adaptability, both economical and potentially very impactful.
That's a strong case. But the flip side. Some might argue that very flexibility, especially in mass production, can lead to monotonous, uninspired buildings. That coldness isn't always seen as moving. How do architects balance that power with the risk of, boring us? And how does concrete stack up aesthetically against traditional materials like wood or stone? What makes it unique?
That's a fair point, and it highlights concrete's duality. Its versatility is its superpower. But yeah, in the wrong hands, it can be misused or value engineered into something dull. The coldness people associate with brutalism wasn't necessarily the material's fault. It could be design choices or sometimes just neglect and poor maintenance later on.
So it depends on the execution.
Absolutely. Look at architects like Tadao Ando in Japan. He uses raw concrete too, but the effect is totally different. Incredibly smooth, almost silky surfaces achieved with painstaking formwork and pouring.
Right, his Church of the Light.
Yeah.
Stunning.
Exactly. He uses concrete to sculpt light and shadow, creating spaces that feel serene, spiritual. He elevates the raw material through sheer craftsmanship and design intent. It's definitely not cold.
Okay, so it can be refined. How does it compare to wood or stone then?
Well, thinking about how buildings learn, wood is lovely, adaptable, full of tradition, easy to work, can be beautiful, but high maintenance, moisture, pests. A typical wooden house might last 75 years without major work. Timber frames protected from weather do much better, obviously.
And stone or brick?
They offer that feeling of solidity, permanence, endurance. Think of old European cities.
Right, built to last.
Concrete offers this unique blend. It has the enduring, monolithic quality of stone, but with a formability that often beats wood for complex shapes. And its aesthetic identity is just incredibly broad.
How so?
Well, you can leave it raw, exposed, béton brut, showing its industrial honesty, or you can finish it in countless ways. Polish it like terrazzo, stamp patterns onto it, stain it, paint it. You can make it mimic smooth marble or rough stone, even wood grains sometimes. The range is unparalleled.
So it can be a chameleon.
It can. And that tension between raw utility and refined art, that's its unique thing. It can be the simple foundation, the footing formwork buried underground. Or it can be a highly visible architectural feature, like those exposed concrete slabs that serve as energy sinks for sustainability.
Ah, functional and aesthetic.
Exactly. Architects can specify different finishes to expose the aggregate inside the little stones by sandblasting or bush hammering. Creates amazing textures, add pigments to the mix for color right through.
So endless possibility.
Pretty much. This duality, basic foundation, and high art, raw and refined, functional and expressive, that's what makes it a true wonder material. Makes you wonder, if the Romans had our modern techniques, what would they have built? Flying cities, structures touching the clouds, who knows?
Okay, we've painted a picture of concrete as this incredible, versatile, strong material. From Rome to modern architecture. Indispensable, really.
Hard to imagine our world without it.
But there's always a but, isn't there? For all its wonders, concrete, or rather its key ingredient, cement, comes with a pretty hefty environmental price tag.
That's the big elephant in the room.
What does this actually mean for the planet, and how urgent is this problem?
It's a huge question, and probably the biggest challenge facing the whole construction sector right now. You look at sources like Designing Reality, they talk broadly about how our material consumption, driven by digital fabrication and just building more stuff, is putting untenable stress on our environment.
And concrete is a big part of that consumption.
A massive part, specifically making Portland cement. There's a chemical process called calcination heating limestone to convert it to lime. That process itself releases enormous amounts of CO2. On top of that, you need immense energy to heat the kilns up to maybe 1,450 degrees Celsius.
Wow, that's incredibly hot, burning lots of fuel.
Exactly. Fossil fuels, usually. Add it all up, and cement production alone is responsible for something like 8% of global human-caused CO2 emissions.
8% from
Right.
just one material.
Yeah. To put it in perspective, if the cement industry were a country, it'd be the third biggest emitter on the planet, right behind China and the U.S.
That is staggering. I had no idea it was that high.
It's significant. And fundamentals of building construction gives us a metric, the embodied energy. That's all the energy used to extract, process, make, and transport the stuff. For concrete, it's around 200 to 300 BTU per pound.
Which sounds abstract.
Ah,
But when you multiply it,
exactly. Multiply that by the billions of tons of concrete we produce every year, way more than any other man-made material. And the total energy use, the carbon footprint, is just enormous. So reconciling this essential material with, not wrecking the planet, it's not optional anymore. It's critical.
okay, a truly stark reality check. If it's so essential and we're building more, not less, how do we possibly keep using it without making climate change even worse? What are the solutions? What's happening on the cutting edge to make concrete greener? It feels like a make or break moment.
It really does. But thankfully, there's a lot of innovation happening. Our sources highlight several promising paths forward. It's about rethinking the whole life cycle.
Okay, like what?
Well, one big area is using waste materials. Instead of just using virgin raw materials for cement, the industry is increasingly using what are called supplementary cementitious materials, or SCMs.
SEMs, like what?
Things like fly ash from power plants, slag from iron furnaces, copper slag, foundry sand, basically industrial byproducts. Fundamentals of building construction lists quite a few. Fundamentals of residential construction mentions using fly ash in things like CLSM or flowable fill.
So using one industry's waste in another product.
Exactly. These SCMs, especially fly ash and granulated blast furnace slag, can replace a significant chunk of the Portland cement in the concrete mix. Many of them have pozzolanic properties, like that Roman ash.
Reacting chemically to add strength.
Right. So you reduce the need for new cement, cut emissions, and you divert industrial waste from landfills. Win-win-win. There are also new types of binders being developed, like LC3 limestone calcined clay cement, showing huge promise for lower carbon footprints.
Okay, so change of the recipe. What else?
Local sourcing sounds simple, but just using concrete made from locally extracted materials and local processing plants makes a big difference.
Reduces transport emissions.
Dramatically. Concrete is heavy stuff. Trucking aggregates and cement long distances burns a lot of fuel. Keeping supply chains short and regional has a direct positive impact. Plus, it helps local economies.
Makes sense. Anything about how we use concrete in buildings?
Yes, designing for functional sustainability. Sustainable construction green building design mentions using exposed concrete slabs that serve as energy sinks.
Energy sinks. How does that work?
Concrete has high thermal mass. It absorbs heat slowly and releases it slowly. So exposed concrete inside a building can help buffer temperature swings. It absorbs heat during the day, releases it at night.
Reducing the need for air conditioning and heating.
Exactly. Lowering the building's operational energy consumption over its entire life. We're also seeing things like ultra-high performance concrete, UHPC. It takes more energy to make per pound, but it's so strong you need much less of it for the same job. So the overall embodied carbon can actually be lower.
Interesting trade-offs. It was about the mix, the transport, and the design. What about capturing the emissions directly?
Yeah, that's another exciting frontier. Carbon capture and utilization, or CCU. Developing tech to grab the CO2 right from the cement kiln chimneys before it gets out.
Okay, capture it. Then what? Store it somewhere.
Sometimes. But even cooler, some companies are figuring out how to inject that captured CO2 into the fresh concrete mix while it's curing.
Injecting CO2 into concrete.
Yeah, the CO2 reacts chemically and becomes permanently locked away within the concrete structure itself. Mineralized. It doesn't just store the carbon, it can actually make the concrete stronger in some cases.
Wow, turning a problem into part of the solution.
Exactly. And then there's the circular economy angle, thinking about what happens at the end of a building's life. Instead of sending demolished concrete to landfill,
Crush it up and reuse it.
precisely, use it as recycled aggregate in new concrete mixes or as base material for roads, reduces the need to quarry new stone, cuts down on landfill waste, closing the loop.
So lots of different approaches working together.
And if you connect all this back to that idea of thinking in systems, it reminds us perpetual growth in a finite world just isn't possible. We have to decide what limits to live within.
Right.
For concrete, it means moving away from that linear take, make, dispose model towards something more circular, more regenerative, constantly innovating to lessen the impact while still getting the benefits of this incredible material. It's like we're still discovering the secret life of this stuff, this complex, almost living rock we've created. Hashtag tag outro.
What an incredible journey today, really diving deep into the soul of concrete. We started way back with Roman ingenuity, their mastery of structure, volcanic ash, arches, vaults, building things that still stand.
Truly foundational work.
Then we jumped forward, saw how Portland cement revolutionized everything, understood the dynamic chemistry of hydration, and how reinforcement, that synergy with steel, unlocked its modern potential.
Allowing those incredible spans and forms.
And we saw it not just as structure, but as an architectural medium, capable of raw brutalism, but also refined artistry. So versatile.
From basic function to profound expression.
But then, the crucial part, confronting its environmental impact, that huge carbon footprint from cement,
Yeah.
and exploring the wave of innovation trying to fix that. SCMs, carbon capture, circularity.
A necessary reckoning.
Indeed. Concrete is so much more than just stone, sand, and paste. It really is a testament to human ingenuity, our drive to shape our world, our evolving science. And its story, as you said, is far from over.
No, it's constantly being rewritten.
Which leaves us with a big question, doesn't it? As we keep building, innovating, and facing the urgent reality of climate change, how do we square concrete's essential role with the absolute need for a sustainable future? What's our responsibility as people living in this concrete world to demand and support these greener materials and practices?
It's a question for all of us.
It really is.
Yeah.
Something to think about next time you walk on a sidewalk, cross a bridge, enter a building. Because the future of our planet is, quite literally, being poured and set, one concrete slab at a time. And we all have a stake in how that story continues.